Okay. So thanks to the organizers for the invitation. It's a really nice conference, except that I'm teaching 2 classes, so probably I won't be able to come for the rest of the meeting, or maybe one more day. So let's start with an Eder-Shreni random graph. N vertices, any two are connected by an edge with probability p. And there's a reason I'm using capital N, because I'll have little n for something else. And you consider this question: suppose T is the number of triangles in this graph, and what is the behavior of this tail probability, that the number of triangles is, some fraction bigger than the expected number of triangles as n goes to infinity, and this delta remains fixed. And p can go to 0 or not go to 0. We'll see. So the understanding this was this thing was open for a long time. As I'll give you a bit of the history, it's still not fully resolved. This problem falls in the intersection of a number of topics in probability theory and combinatorics. So that's what got me interested in this. So the reason why it's surprising that it's difficult is that it's just a degree 3 polynomial of independent random variables. If you consider the edges of the graph as your independent random variables, the number of triangles is just a polynomial of degree 3. So why should it be complicated computing this kind of tail probabilities? Okay. So there were a long list of papers with improving bounds, and then finally this was almost optimal. Kim and Wu and Svante Jansen and co-authors, they proved these optimal bounds. So if p is at least log n over n, then this probability is like e to the minus n squared p squared upper bound and n squared p squared log 1 over p lower bound. And these are constants that depend on delta. Okay, so this result came after a lot of effort by various people, and so for instance, if you just apply the Asimov-Hofstring, the bounded difference inequality, you're getting you'll get a very suboptimal bound, and then you try to improve that and keep on improving until you reach here where you have this gap. And then I had this paper, and also Jeff Kahn and one of his students had this paper where this logarithmic gap was closed. So this is actually the right order. But the constant exponent, how does it depend on delta? That's a large deviation question. Okay, so this is concentration of measure, concentration inequalities. But if you want a more precise answer, what is the probability up to little o of 1 in the exponent? So this was still open. And when p is fixed, so I had a paper with one of my students, Part today, where we used a version of Stein's method for concentration inequalities to compute this constant in a range of p and delta, but not for all values. So you could do it only in a small kind of range. And then there was this paper afterwards that I had with Raghu Varadhan, where this was this constant, again for fixed p, when p is fixed, you're considering dense graphs, you have this constant exact evaluation of this as a solution of a variational problem. Okay, and this formula was conjectured in this earlier paper, which Amir, yes.
So you said that was close the gap, but the right one is what, the upper bound?
No, this is the right one. This is the right one. Okay.
Yeah, quick question. What is the variance? Is that Gaussian with the correct variance on the exponent? Or n squared p squared is the variance of...
n squared p squared. So this, so this side, where this lower bound comes from, is by just constructing a clique. So suppose you get all these extra delta times expected. So the expected number of triangles is like n cubed p cubed times something. Okay. So this extra n cubed p cubed triangles you can construct by just taking a small collection of np vertices and connecting them all together by edges. So this small collection, this is the cost of that such a clique occurs, and that's how you get the lower bound. And it turns out that that's the right order. That's the correct thing that gives you. Although, as we'll see, just the fact that you have these extra triangles doesn't mean that you have a clique. So this is the, to understand such refined questions, you have to know what these constants are somehow, where these constants are coming from. Because you can have the same lower bound by some other techniques also, not just by building cliques, by doing some other things.
So what is the most probable process in the random graph? Is a quasi-clique?
We'll see that. So yeah. Okay. So in the dense case, when P is fixed, this constant in the exponent was evaluated as a solution of a variational problem. It was conjectured here, and actually Amir is the one who told me about this class of problems when I was a student at Stanford, and they had this paper, and they did it for some subgraphs which do not have cycles. And the proof of this in this paper relied on the regularity lemma and the theory of graph limits. So this is what it used, but I'll not have time to talk about this today. However, this lemma has no satisfactory analog for sparse graphs when P is of order n to the minus alpha for some positive alpha. When P is decaying like a polynomial in n, there is no satisfactory analog, and there is what I mean by this. I'll not I mean basically you don't have a counting lemma. That's the problem. So this made it impossible to extend this proof to the sparse case. Okay. Now here is the partial solution. So here is the result that Lubetsky and Yufei Zhao proved a couple of years ago. If n goes to infinity and p goes to 0 slower than n to the minus 1 over 42, okay, then this probability behaves like this. The chance that the number of triangles exceeds the expected number by a fraction delta decays like e to the minus delta to the 2/3 over 2 and delta over 3 n squared p squared log 1 over p. Okay? And this constant here encodes what happens. So it can happen in two different ways. One is by a clique, which I believe is this term, and the other is that I don't remember clearly, is that you can have a set of vertices which are highly connected to everything else. So there are these two competing ways that you can have this, and one of them wins out depending on the value of delta. Okay. Now, and the conjecture is that this formula is valid if p goes to 0 slower than n to the minus a half. You don't need n to the minus 1 over 42. And so why do you get this very bad exponent? It's because this proof uses this theory that I'll describe in this talk of nonlinear large deviations that I have with Amir. So we gave the solution, this probability as a solution of a limiting variational problem. And Eyal and Yufei, they were able to actually solved that explicitly and got this answer. So that's how it worked. And I'll describe this theory where this how this kind of results are derived. Okay. So, but any questions about this? So this formula, as I told you, it tells you more. It's more than just a formula. It tells you what's the most likely structure of the graph, and this can get rapidly, it can get more complicated. So there has been a recent generalization of this. I'll show you in the next slide. So it's for counting arbitrary graphs, so not triangles, maybe something else. So take any connected finite simple graph H on k vertices and maximum degree bigger than or equal to 2. And we'll see the large deviations for this one. So it requires a little bit of preparation. Let H star be the induced subgraph of H on all vertices whose degree is exactly equal to delta. Okay, so if H is a regular graph, then H star is just H. Define a polynomial. It's sort of like the independence polynomial. Define a polynomial related to this graph as summation x to the k times the coefficient. The coefficient of x to the k is the number of k element independent subsets of H star. Okay, so it's just defining a polynomial. And for instance, if H is C4, then the degree is the largest number of k element independent set is 2, so it's a degree 2 polynomial. It's just a quadratic, x goes up to x squared. So it's a low degree polynomial depending on the small graph H. And then you consider the number of homomorphisms of H into G and P, which just means the following. It's a map from the vertex set of H into the vertex set of G and P that preserves edges. Okay, so it's slightly different than counting the number of copies, but it's almost the same. So for instance, if H is a triangle, this is just 6 times the number of triangles in GNP. Okay, and this is this number of homomorphisms is very convenient for many purposes, and it's the basic object in the theory of graph limits. And you can, if you want to count the exact number of copies of H, that H occurs as an induced subgraph in GNP, then you can use this homomorphism, some linear combinations of homomorphisms, and recover that eventually. But anyway, so this will be our object of interest, the number of homomorphisms of H into GNP.
Is it really injective though?
No, it need not be.
If it's a 4 cycle, you can have an edge as a copy.
So it need not be injective, but it needs to be edge preserving. So you know, two vertices can go to 1 if there is no edge between them. If there is an edge, then they cannot go to 1. I think.
So a 4 cycle could just map to an edge.
Probably. So yeah.
But normally the number of 4 cycles that map to edges will be dwarfed by the number of 4 cycles that map to 4 cycles.
Yeah. So it's basically, you know, it's counting. So anyway, this is the setup, and so this H is a graph, and then you take the induced subgraph by throwing away all vertices whose degree is less than this maximum degree, and then define this polynomial, which is a low degree polynomial, then this, and this is the result. That is the recent one by Bhattacharya, Ganguly, Lubezki, and Zhao, 2015. They generalized this earlier one. For any positive delta, you take some fixed positive delta, you want to understand this probability. You first solve this equation, P H star theta equals 1 plus delta. Okay? So P H star is the sort of independence polynomial that I defined. So the independence polynomial of the H star graph. And then there is a constant alpha depending only on H. So they were, I think, too ashamed to write it down, actually. So it's like 1 over 42, but worse than that. So there is some constant alpha, so that if p goes to 0 slower than n to the minus alpha, then this probability behaves like n squared p to the maximum degree. So delta is the maximum degree, log 1 over p times a constant depending on delta, where the constant is theta if h is irregular, where theta is this theta, which solves the equation, and minimum of theta and half delta to the 2 over k if h is regular. So k is the number of vertices in H. Okay, so this is the exact solution. And for instance, if H is C4, we have already seen H a triangle. Just another example, if H is C4, then the C delta is half root delta if delta less than 16, and minus 1 plus square root 1 plus half delta if delta is bigger than or equal to 16. Okay. So in all examples, so this formula, how it comes from is, you know, is in terms of a solution of variational problem, and you have to understand where the variational problem is maximized. So that will dictate the structure of the graph. And in this paper, they have some detailed discussion of what it means. You know, if this is bigger, or, you know, if theta is bigger than this, or if this is bigger than theta, what's the structure of the graph? You know, it has some meaning. But not very concretely, because sparse graphs, we don't yet have a theory of graph limits for sparse graphs. So it cannot be said in a very precise way, but it gives an indication of what the structure is. Any questions about these results?
So how should we think about this condition that p goes to 0 slower than something? Is that like a feature of the theorem or a bug?
So for instance, in this previous result, you see probably the answer is different if p goes to 0 faster than to the minus half. Okay, because the variational problem that, you know, Eyal and Yufei are solving, it has a different solution. So probably the answer is different. So you need to have some threshold for this kind of result to be valid. But the threshold that you get from the technique that I'm going to describe is probably very suboptimal. This n to the minus 1 over 42 or whatever n to the minus, that is very suboptimal. So that's one open question, that, you know, how to have a more effective or efficient theory that can have, you know.
Like the best thing would be to have like a formula for every rate of p, or
yeah. So that there is a formula. So I'll tell you. So that there is a variational formula which I believe should hold for any p going to 0. Well, not 1 over n. So 1 over n comes to the bounded degree kind of graphs, which is sort of a different regime. But other than that, it should, or at least, you know, log n over n should be okay. Okay. Okay, so let me start describing the general problem. So take any smooth function on the cube, n-dimensional cube, and let y be a vector of IID Bernoulli random variables. And we want to find an approximation for this kind of upper tail problem. So the probability that fy is bigger than or equal to t when t is much bigger than the expected value. So, t is some fraction bigger than expected value of fy. Classical large deviations theory will tell you what to do for linear f, but for even very simple nonlinear f, like degree 3 polynomials, it can get very complicated. And the question that motivated the work that I'm going to describe is that can there be a more unified approach? And there will be something of interest to all the physicists here also. So it's related to the mean field approximation. So I'll let me go into that. Okay, so is the setting clear? You have a function, you have a bunch of IID Bernoulli random variables, and you're asking about this question. Okay. Now you define a function IP on this cube as summation xi log xi over p plus 1 minus xi log 1 minus xi over 1 minus p. And for each t, you define this function phi p of t as the infimum of this entropy-like thing over all x where fx is bigger than or equal to t. Well, t actually it should be t, not t. Okay, there's n missing in the previous slide. So you take this thing, and in many problems it turns out that this tail probability is approximately e to the minus this quantity, the minimum entropy over the region of interest. Okay, you take the entropy and you minimize the entropy over the region of interest, and you get this answer. And this is true in great generality for linear functions. The question is, when is it true for nonlinear functions? So it turned out that for the case of fixed p, if you consider the triangles in Erdős-Csörny graph for fixed p, this approximation is actually valid. That's what comes out from Samaridy's regularity lemma. Okay, the regularity lemma, using the regularity lemma that we showed in this paper with Raghu, we showed that this approximation is valid for large n. Okay. Now the question is, when is it true for general f? And as I said, if you use the regularity lemma, first of all, it's very specific for a certain kind of problems. Okay, problems coming from graph theory or having some connection to graph theory. And secondly, you cannot go, you cannot work with small p. Okay, so the question is, can we have some kind of more general theory that will give a sufficient condition for this to be true? And I call this the naive mean field approximation here because it has to do with that. So, there's this thing called the naive mean field approximation that statistical physicists do sometimes, and it's a version of something like that. Okay.
So, yes. So I take it this is sort of obviously right if f is a sum of n independent functions, or?
Yeah, if f is any linear function, f is a sum of yi. So y is a vector of IID Bernoulli's. Y is y1, y2, yn. So if it's a linear combination, then this is true. Right. Now the question is if you have a nonlinear function.
Classic large deviations.
Yes, that's the classical. So that's why this I call this nonlinear large deviation. Yes.
So here, like in this phi definition, you're sort of optimizing over all product distributions. You can think of you think of x as a product distribution.
Well, okay. So of course the underlying y is a product distribution. Now the question is, so what? So your intuition is right. So what is the product distribution that you're talking about? So we already have some product distributions, but then what exactly is the product distribution that we are talking about? And that's that's the question. So let me come to that, and maybe it'll be more clear. So here is the main result. It's a rough statement of the main result. The approximation that I showed is valid. There's a sufficient condition. So in addition to some smoothness conditions, you need some smoothness on f, where all this suboptimality comes from. So I can only work with smooth functions, or smooth to a certain extent. The main condition is that the gradient vector, if you take the gradient of f, del f del x1, del f del xn, this may be approximately encoded by little o n bits of information. So it's, it's a condition under which the naive mean field approximation can be, so physicists use it, but there is no general condition that's anywhere written down as to when is this naive mean field approximation, when can you expect this to be true. And this gives a general condition that the gradient can be approximately encoded by little o n bits of information. I'll tell you more, what this means. So I'll give you, demonstrate through some examples what this means. So we call this a low complexity gradient condition. And the actual statement of the theorem, I'll show you one version of the statement later on. It's somewhat messy, and that's where you get those bad exponents. Here's another note that there are many sharp upper and lower bounds for the tail which match up to constants in the exponent, and but I didn't see any results about this precise approximation. And there was some preliminary work in this paper, but which kind of led to this one. Okay. So now I'll tell you what this means. That if you have a function f, so again, this is the general thing that maybe I can give to the physicists here, is that when you're applying this naive mean field approximation to some function f, this seems to be the right condition somehow, that this gradient can be approximately encoded by little o n bits of information. So I'll tell you some examples. So for instance, this is the Hamiltonian of the one-dimensionalizing model, xi plus 1. Here is not valid. So if you take the gradient, del f del xi, it's xi minus 1 plus xi plus 1. So if you want to encode the gradient vector, the value of the gradient vector, you have to essentially know all the xi's. If you don't know all the xi's, you cannot approximately encode it. Okay, so that's why the condition doesn't apply to this one. Okay, to encode the gradient, even approximately, we need to know almost all the values of the xi's, and the mean field approximation is not valid. However, if you consider the Hamiltonian of the Curie-Weiss model, then del f del xi is minus xi over n plus the whole average, the average of all the xj's. So therefore, the gradient vector, it's a vector of n components, and the ith component is this one. So up to an error of order 1 over n, you can encode the components by the single quantity. There's a single quantity, that encodes the full vector approximately. And to encode a single quantity, you need log n bits. It can take n possible values. So again, the large deviation approximation is the approximation that I showed is valid. So this is an example where the low complexity condition for the gradient is satisfied. Okay. Now this is a simple example, and you can do many examples. So if you consider the Ising model, but with kind of longish range interaction, then you can have the same thing. So you can just take the gradient and show it can be approximately encoded by little o of n bits. Now the complication comes when you take the number of triangles. Okay. So let's see. Let's do this example. Let t be the number of triangles in the Erdős-Srény graph. So t, how do you write it as a function of independent random variables? You write it as summation yij, yjk, yki, where this is the indicator that the edge ij is present in the graph. So it's a degree 3 polynomial in n choose 2 random variables, IID random variables. And then you can put this in the setting of the theorem by taking little n to be n choose 2, because there are little n IID random variables, and then f, and denote the elements of Rn as xij, as these matrices, and define a function f like this. Okay, so then you're in the setting of the theorem. So this is the function. This is a nonlinear function to which we want to apply the mean field approximation. Okay. So you see, so what physicists would say that each so ij, take an edge ij that's like a location of a spin, and it's influenced by a whole bunch of spins, but this whole bunch of spins is not all the spins, or not even a large fraction of the spins. It's 1 over n fraction of the spins. So it's not clear whether the mean field approximation is going to apply by a physical heuristic. But we'll see that this low complexity gradient condition is valid. So if you take the derivative of f with respect to xij, this is exactly what you get. It's basically the fraction of common neighbors of I and j. Okay? So if you take any I and j, look at the number of common neighbors of I and j, okay? Divide by n, so you get a number between 0 and 1, multiply by 3, that's okay. So to each edge, you're attaching a weight, which is between 0 and 1, which is the number of common neighbors of the two endpoints divided by n. Okay. Now the question is, so this is the gradient. This is the gradient n choose 2. N choose 2 numbers between 0 and 1 that you get. The question is whether these n choose 2 numbers can be approximately encoded by little o of n squared bits. Okay. So that I claim that that is possible. Okay. That's the main reason why the mean field approximation works for this for the number of triangles. Okay. So so the key observations are the following. How you get this result is that if you have two symmetric matrices which are closed in operator norm, then you can show that these aij's that you obtain from these two matrices are actually closed for almost all ij. So if two matrices are closed in operator norm, it doesn't mean they're element-wise closed. But if you take, so this is basically the ijth element of the square of the matrix. So if you take the squares of the two matrices, then they're element-wise closed. Okay, if two matrices are closed in operator norm. That's the first observation. The second is that if you want to approximate a matrix in operator norm, it's this is the number of bits you require is little o of n squared. Okay, you don't need. So if you want to approximate in the Hilbert-Schmidt norm, if you want to approximate element-wise, then you need n squared bits because you want to have a code for each entry. But for operator norm, you don't need that. And that's because the entries are bounded in 0, 1. So what that means is that the sum of squares of the eigenvalues is n squared, okay? Which means that the kth largest eigenvalue is bounded by n over square root k. You can have that kind of an estimate. So you can throw away all eigenvalues after some stage, all eigenvalues and eigenvectors, and you can keep a little bit, okay? And that suffices to encode in operator norm. So if you keep a little bit in the spectral decomposition, you throw away most of the eigenvalues, the rest can effectively encode the matrix in operator norm in the sense that you can find these many matrices so that any matrix that you give me is close to one of these in operator norm. Okay? So using these two facts, you can show that these numbers can be encoded by little of n squared bits. Yes?
Maybe I don't know what you mean by encoded, because it seems like if the graph is sparse, then the entire graph can be encoded in little o of n squared bits. But that doesn't count as an encoding in this case?
Okay, so I was just trying to give you the intuition. So I'll give you the main theorem, and then it'll be hopefully it'll be more clear that what I mean by that. So certain things will get worse if you send p to 0, and those are the smoothness estimates that I was. So I told you that the function f needs to be smooth, and well, it's not only f. So what I'm using here is f times the density of the graph. It's somehow you have to put that in, and the density of the graph involves a p, and p will destroy the smoothness as you send p if p is too small. So those kinds of issues. So let me.
Wait, one quick question. So if you had a dense graph, you applied regularity lemma, then you get that the codegrees between two parts will be roughly the same, right?
Yes.
So that would be a constant number of bits or whatever approximation.
Yes, but the thing is, when you apply the regularity lemma, well, so first of all, this is a very crude version of the argument of the proof of the weak regularity lemma, where you just throw away something and you want something in the operator close in the operator norm, and it turns out that somehow this crude version, so the regularity lemma gives you something much more powerful, but we are just interested in the behavior of, let's say, triangles. Just you fix some subgraph, just in the behavior of triangles. So somehow you don't need to use the full power of the regularity lemma. If you use even the weak regularity lemma, even if you use its full power, you can go only p like some negative power of log n. You cannot go to n to the minus. So somehow the main theorem that I'm going to show you after just a little while later allows you to tailor your argument to a specific f, rather than having a general result for all subgraphs. So that's where the gain comes from. So here's the example. What's the precise result for triangle counts? So you recall this function IPX, and recall this TX, and then you define this this psi p of u as the infimum of the entropy over all x such that Tx is bigger than u times expected value of t. And so here is the result. So this ratio minus log the probability that t exceeds its expected value by u, and this variational formula, the ratio of these two things is bounded above and below by 1 plus or minus errors, and the errors are like this, okay? And this is where this thing comes from, that if n goes to infinity and p goes to 0 slower than n to the minus 1 over 42, then this ratio will go to 1. Okay. And then what Eyal and Yufei did is they actually understood that this variational formula has this nice explicit computation in the limit. So but their proof holds even if p is going to 0 as fast as n to the minus a half. So they could analyze psi p of u even in that. So this is the result which causes the n to the minus 1 over 42. Okay, so it's our fault. Okay, so here's the main result. Let me try to show you the main result about the nonlinear large deviations, and we'll see where things are going wrong. So take any function f from 0, 1 to the n to r, and let norm f denote the supremum norm. And let fi and fij be the first and second partial derivatives, and a, bi, and cij be all the supremum norms. And then this is the crucial object. Let d epsilon be a finite subset of Rn such that for every x, there exists some element here which approximates the gradient vector. So you take the gradient vector f1x through fnx, and for every epsilon, so let d epsilon be a finite subset which approximates this up to some error. Okay, so you're trying to find an epsilon net for this, the image of 0, 1 to the n under the gradient map. So the gradient f maps 0, 1 to the n into something, into Rn, and you want to find an epsilon net for that.
There should be some scaling there, right? I mean, the norm of f, because right hand side.
Yes. So okay. So the theorem, the statement of the theorem, well, just gives you everything in terms of these numbers, and the scaling comes in implicitly. Okay. So let Ix be this entropy, and let f be the log of the partition function, log of e to the f, summation e to the fx. So I'll try give you a formula for this thing, and this can give you formulas for probabilities. So if you suppose you're trying to compute the probability of some event under Bernoulli measure, so you write it as e to the fx. So fx will have one component which is a log of the probability of a configuration, and the other component is minus infinity if you're outside the event and 0 if you're inside the event. So you can transform any question about a probability into a partition function of this form. So by the way, the standard large deviation technique of computing moment generating functions and optimizing over theta, that doesn't quite work for this class of problems. So you have to go more directly. So you have to just take this, and instead of approximating indicators by exponentials, that's what you do in usual large deviations, you approximate indicators by smooth approximations of indicators. Okay, so that's what needs to be done. But let me give you this formula. Then we define these two terms. One is the smoothness terms, which involves all the smoothness coefficients that I wrote down, and the other involves this the size of these epsilon nets, which measures the complexity of the gradient. And then once you have these, don't even have to look at it very carefully. You have this result that the partition function is bounded by the supremum. So this is the approximation. This is the mean field approximation. Fx minus Ix over all x plus these complexity and smoothness terms, and lower bounded by something similar. Now, in statistical physics, you often have the naive mean field method involves some set of equations, mean field equations. So there are no equations here. So what's happening is that when you are computing the supremum, Well, if you want to actually compute this, maybe you have to solve for the variational problem. You have a set of Euler-Lagrange equations, and those are exactly the mean field equations that you would get as a physicist, in the naive mean field approximation. These Euler-Lagrange equations of this supremum problem. Okay. Okay. So this is the main result. Any questions about this?
Could you remind us what's capital F?
Yeah, so capital F is this.
Okay. And why is that telling us
Why is that telling you about the large deviations?
Yes.
Yeah, the large deviations, so what you do is that, okay, so suppose you want to ask what's the probability that number of triangles exceeds something. So then it's a sum over a subset of this space times the probability of each element, px times it. Now this subset is the indicator of the subset. You approximate it by a smooth function, so e to the power of a smooth function, and then you go like that. Okay, so that's how this is done. Okay.
So one question here. This Ix is Ipx.
No, there is no p here. There is no p here. It's general. So the p is hidden in this f.
Yeah.
So that's what I was saying. What goes wrong if p is small? This f starts behaving badly if p is small. Okay. So the smoothness terms become kind of bad. Okay. So do I have any time at all? Or? Okay. So let me give you very quickly, in 5 minutes, let me see if I can give a sketch of the proof. So what you do is you first start with a random vector that has probability density proportional to e to the fx on this hypercube. Okay? Then you define a bunch of functions, xi hat, I equals 1 to n. Xi hat is the expected value of xi given the rest of the coordinates. So xi hat and x hat is a function that takes all of these together. Okay? And then capital X hat is little x hat applied to x. So you have a configuration x1 to xn from this probability measure, and then you convert it to a new thing where the ith coordinate is the conditional expectation of the ith of xi given everything else. Okay, so this may be a highly non-trivial nonlinear function of the xi's. The first step is to show that fx is close to fx hat with high probability. Okay, under this measure. Given the smoothness, this is only the smoothness conditions play a role here. That fx is close to fx hat. So in f, you can put in place of the xi's, you can put in the conditional expectations. The next step is to take a function g defined like this: gxy is summation xi log yi plus 1 minus xi log 1 minus yi, and then you show that you can do the same to g. Gxx hat is approximately with high probability gx hat x hat, which is just ix hat. Okay? Now suppose these two steps have been proved. Let A be the set of all x where fx is close to f x hat x and gx x hat x is close to I x hat x. So it's like these two conditions are satisfied. So that your original random vector x belongs to this set A with high probability. So then with high probability you have this, you have x belonging to A, which just means this is true. Okay? So this means that this f, which is the original partition function, is close to sum over log of the sum over a e to the fx. Now since fx is close to fx hat x, you can put it in here. And since 0 is close to this difference, you can put this in over here. So you can replace it by this much more complicated function. So you had fx originally. This is a much more complicated function. Now what you do is you take epsilon to be a small positive number. And using the low complexity gradient condition, you can find a smallish set of points so that for any x, the vector of conditional expectations is close to some element of this set. So this vector of conditional expectations that you get at each vertex, this vector, is approximable by a small set. So there is a e to the little o n size set, so that for any x, x hat x is close to that. Okay? Okay, so I'm sorry I'm running over this now, but now for each p, you let script p of p be the set of all x such that x hat x is close to p. Okay, And the crucial fact is that if you take summation e to the gxp, that gives 1. So anyway, so you had this, okay? You replace your original thing by this complicated function. Now this, you write it in this way. Now the thing is, you can replace this x hat x by one of the elements, by a constant vector. So this is the upper bound. You can replace, now that x hat x is close to p, you can replace it by a constant vector. And this you can sum up because of this identity. So you can have this sum, and you can bound it by this thing. And the main thing is that log of d prime epsilon, that's little o of n. So yeah, this is very bad. I know nobody's following, but yeah. So okay. I can go back now and tell you a little bit more in case. So the reason why I'm showing this is that this result is highly suboptimal. That is, you can go into the -1/42. So it really needs improvement. You need to have a result that can go all the way up to the a much nicer result with a nicer error bound, and which goes all the way up to the optimal sparsity. So first of all, that's the first reason for showing this. The second reason is that I don't quite understand why this works. Okay, so I understand how the similarity lemma argument works, using the regularity lemma in the dense case, but why this one works, I have, I don't really understand. So let me go back, since I have maybe a couple of minutes. Let me go back and let's go over this this proof once again. So what you do is you start with a random vector x, okay? Well, even if that makes at least one person happy. So you random vector x, which has density proportional to e to the fx, and then you take, what you do is you take the vector of conditional expectation. So on each coordinate, you take the conditional expectation of xi given the rest. So you have this. And then you define this function gxy to be like this, and then you also try to show this. So these, I haven't shown how these things are proved, okay, how these two steps are proved. And then you look at, you restrict your sum to the set where these identities are satisfied, okay? And then you convert your original partition function, log partition function, into this more complicated thing. And finally, you try to replace these complicated functions by constants, which you can do because the vector of conditional expectations, although it's not a constant, it's a complicated function, it cannot take too many different values. So you can replace it by constants. So that is sort of the idea, what happens now. I'll not do this. So how you get fx equals fx hat. So that's another different kind of argument. So anyway, here's a summary. So large deviations for sparse graphs, these cannot be tackled by techniques based on graph limit theory and Semiradis lemma, at least not in a way that I know of. The theory of large deviations for nonlinear functions of Bernoulli random variables has seen some successful applications. So there were some questions that were open for a long time, and now we know at least if it's not too sparse. And the main problem is the degree of sparsity allowed by these theorems is much less than optimal. And this is where you need these new breakthroughs, or and improved results to tackle this kind of thing.
I think it's difficult for me to understand the whole thing, but here's a little question, right? The epsilon net argument, suppose I gave you that the gradient at just one of those values exactly. Is it easier to explain what is going on? And there's one part where you approximate by epsilon net, another part where you use epsilon net, right?
Yeah, so, okay. So the thing is, I've been trying to understand this. Yeah, if I had a better way, I'd have said that. But let me try still make an attempt. So what happens here is that somehow in this approximation, I'm replacing f by this function. Okay, and if you look at the form of g, what g is, okay, g is this function. So if you imagine x hat to be a constant, then this just becomes a linear function in x. Okay, so it's sort of a piecewise linear approximation of f. Okay, but f is not really piecewise linear. F is if the number of triangles, it's a cubic polynomial. It's not piecewise linear. But what this is saying is that with high probability, f equals one of a bunch of piecewise linear functions in some sense. Okay, so this happens with high probability, but that's not sufficient. I have tried to make that proof, make the proof in that way so that ultimately you get some nice result instead of this horrible thing that I showed. So I tried that. I couldn't quite get there. And a very smart student at Stanford, Alex Zari, one of Amir's students, he's also trying for a while to get that. So maybe there'll be something much nicer. But for now, the most meaningful thing I can tell you is what I just sketched over here. And I don't know anything simpler.
More questions?
So you're saying that f is, I guess, not a mixture of the size of D product distributions, but sort of a patchwork of the size of D product distributions in some sense. I don't mean that f is a product distribution. I mean your weighted distribution, your Gibbs distribution, where the probability is proportional to e to the f. That acts roughly like size of D many different product distributions.
Maybe, but well, the thing is, it's all intertwined, right? So as soon as you would like to say that the x size. So if you take, let's say, a probability density proportional to the number of triangles, okay, you would like to say that the edges behave independently given the approximately independently given the gradient. So given the conditional expectation. So given so that's the general mean field heuristic in some sense. But that's certainly not true if you combine everything together, right? So if you take all the xi's together, of course the conditional expectations are themselves functions of the xi's. So it's not clear, how this intertwining happens. So it's so it would be great to be able to figure out exactly what this means in terms of this approximate product distribution or a mixture of product distributions, which is probably correct that it's a mixture of product distributions. But the only difference is that, you see, when you're considering the Curie-Weiss model, for instance, at above the critical temperature, below the critical temperature, low temperature Curie-Weiss model, then there is this one quantity which is magnetization, and if you tell me the magnetization, then conditional on that, things are approximately independent. Okay, but here you have a graph of size n. There are n squared spins, to say, but there are this conditioning thing is also n squared somehow. There's number of common neighbors in each, or the conditional expectation of an edge given everything else, there are these n squared different things. Okay, so, and even if you scale it down, it becomes, it's pretty large. So it's not clear exactly, what, how to handle that. And I've been trying to do this for the last, 10 years. And so.
Thanks again. Here is unit 4.